Hello. Today we want to talk about the idea of a partial derivative in of functions of two variables, uh, real valued functions of two variables, and how discontinuous functions can have partial derivatives. So let's go ahead and get started. Now, one of the things I want to mention, so note, oops, I think I got this right. In Calc 1, uh, having a derivative means being continuous. But it's not having partial derivatives does not mean being continuous in Calc 3, as we'll see for a second. So first, let's start off with an obvious example. Now let's start off with a very, very silly function. Let's say we have f of xy, and f of xy will be 0 at 0, 0. It will be 1 if uh, x equals y and x is not 0. So in other words, if we look at the diagonal and remove this point right here, our function is going to be 1 right along this diagonal line and 0 elsewhere. Now, clearly, f is not continuous. Because we've basically defined this in a really silly way. We jump to the value 1. So along this one-dimensional line here. But if we look at the partial derivative and look at the limit definition at 0, 0, this will be the limit as a change in x goes to 0 of f of 0 plus change in x minus f of, oh, I just screwed that up, didn't I? I've got my calculus mode a little bit too much. And that has to be a 0 here. Minus f of 0, 0 over delta x. Okay. So let's see what we get here. Well, keeping in mind that delta x is not exactly 0, this means that we're in this part of the definition because this is not 0. So this is a limit as delta x goes to 0 of 0 minus 0 over delta x. And that's clearly 0. And similarly, f sub y of 0, 0 is also 0 for the same reason. The difference quotient here would be f of 0, 0 plus delta y minus f of 0, 0 over delta y, when of course we take a limit as delta y goes to 0, and we get 0 over delta y for exactly the same reason. And I better write that as a limit, and that limit is 0 as well. So both partials exist, even though the function has this line's worth of discontinuities, and the limit does not exist at the origin. Now that was kind of a very, very silly example, but there are other examples like that. Let's do a second one, probably a more common one. And here, let f of xy equal the function xy over x squared plus y squared for xy not the origin and 0 for x, y equal the origin. And as we know, first thing is f is not continuous at the origin, because if we take a limit as x goes to 0, 0 of xy over x squared plus y squared, and this is along the line y equals x. This is a limit as x goes to 0, 0. And we have x squared on top because we plug in x for y. On the bottom, we have x squared plus x squared. Canceling the x squares because we're taking a limit. So we can do that. We're not exactly at 0. So you cancel that, we get 1/2. We see 1/2 is not 0. So this function is also not continuous at the origin. But unlike the first one, this one had a whole line's worth of discontinuities. This one here has a discontinuity only at the origin. The second thing, though, is if we look at the partial derivatives, and if we say take a limit as the change in x goes to 0 of f of 0 plus change in x, 0 minus f of 0, 0 over delta x, what happens is that at the top, we have a delta x for x. The y is a 0. The bottom is a delta x squared plus 0 minus 0 over delta x. But this part right here, this is really going to be 0 over delta x squared divided by delta x. And we're taking a limit as delta x goes to 0. So that goes to 0, 0 over delta x cubed, which is still 0. And similarly, this is a symmetric function. F sub y at 0, 0 is also 0. So in this case, both partial derivatives exist. This one here was a proof that f sub x 0, 0 is 0. So both partials exist, even though the function is not even continuous. So that's the second example, and of course, there's many, many others. Thanks for watching.